Hear me. All right, we're switching things up a bit. I put the chat on the right, and then me and my face on the left. Basically because I have a weird obsession with hilarity. I think what is that called? The chiral. I'll get that pronounce it soon. Okay. This Rumble, this Odyssey. Let's see if this works. Usually it's a refresh. Okay, and let's see if this works. This is the that's a refresh. All right, but anyways, guys, let me know if you all hear me. Okay, you're just going live now. Okay, now we're live. Okay. Yeah, I think it's a delay or something. Fast forward. Okay, how's my audio? Okay, can you all hear me in there? Let's see what this says. People saying stuff. Okay. Sound level's a bit low. Okay, so I need to increase that. Yeah, so I found is it's like all these computers, it's like they just don't have like they don't know how to make. Okay, why? Okay, I'm gonna make this why you're right. Okay, how do I go to the sound? Um, sound settings. Okay, so now where does that pop up? It goes here. Okay, I moved everything. Yeah, I moved things to the right. We'll see how it goes. Okay, just because I have I'll explain it. I have like an obsession with everything needs to be like even. Okay, I can't. And I gotta go this way. It helps my brain thinking. It sounds fine to you. Okay, so we have 6 people in the. Okay, there's the input. I'll make it a bit louder then because he's saying it's a bit low. So input volume, microphone. I'm gonna go to like here. Okay, and then output. Maybe like that or something. Okay. Anyways, remember to smash a like. Okay, yeah, smash a like. We'll go over a bunch of stuff. And yeah, thanks for that Bedini motor stuff. Yeah, that's definitely something we need to investigate. So first thing I'm gonna do is send an email because I sent an email to a bunch of peeps, and it's like nobody has like common sense or like actually listens carefully to the words I say. Okay, and there's guys. Also there's a threadcast here. If you guys know how to figure out how to post on Hive, definitely get on Hive. It's again. A lot of people when they hear the word blockchain, it's like just don't realize it. It's like internet. If I was telling you in internet 1990s, just get on it. Especially versus these nonsense like YouTube and other stuff. And also, guys, please donate. The Prism Live Studio that I use, this thingy here, it's charging me like now I can't multi-stream anymore on the free one. So now they started doing it, you have to pay. So it's $15 a month Canadian with tax. So donate and fund this operation. So paying that per month just to be able to multi-stream and so on. It's like that's usually how they get you. They do everything for free, and then all of a sudden they charge it. MSFM/donate, guys. Donate a bunch of cash money to me. You can do either silver or gold. Buy silver or gold. Get affiliate. PayPal. Become YouTube super fan, and you can also donate crypto and other PayPal and so on. Also become super fan, guys. Get custom emojis. Get these 14.99 Canadian. This will pretty much fund. Yeah, once Skyward will fund the subscription that I'm paying for the Prison Live Studio now, and you get these custom emojis, and you guys throw a bunch of cash money at me, and so on, and yeah, all right, so that's that. Okay, so I have a bunch of stuff. Here's a bunch of links we'll go over, but what I first want to do is so here's a bunch of links. I'm gonna go like this. Yeah, I drink I'm just a bit cold right now. I just drank a bunch of cold water. All right, how do I like get this to my face properly? Just because everything's new. 1 second. Okay, so it's like this thing, you just zoom out. Like, why is it so hard? Everything has to be so annoying. Okay, I'm gonna go like this. Whoops. 1 second, guys. I'm trying to do this properly. Okay, so make it like that. Okay, but then I go here. So then I need to make it like this. Okay, I'll make it a bit smaller. Okay, it's like it always goes back to it. I don't understand. What is this machine? Okay, it goes like this. Sorry, guys. I'm trying to figure this stuff out. Maybe if I open it up. So, anyways, guys, I'm still trying to figure out how to use this Mac. I'm like literally in the Matrix right now. Okay. Oh, yeah. Then now it sticks a bit more. Okay, so now I can zoom it back out. Um, it's just I can't zoom out. I can make it like this. Oops. It's like what? I'm in the Matrix, absolute Matrix. Okay, there it is. Okay, there it is. Nothing's free anymore. Yeah, nothing's free. That except the blockchain, crypto. They pay you. That's the thing. On Hive, it's like they literally pay you, and they pay you to post. It seems like Substack will like probably require you to pay and so on, and also like Gmail and all that because they've been storing data for so long. Now it's like they're asking you like you're gonna start deleting their old emails unless you pay. So, and again, compare that with the Hive blockchain. It's like they pay you to post. I can't stress this enough. Hive literally pays you. Yeah, it literally pays you. Compare that with X, you need to pay just to not get like censored and so on. And again, I'm like, I don't know how to stress enough. Just post on Hive and ask questions later. All right, guys. Anyways, guys. Yeah. So we have this. I'm gonna go over. First, I want to show this thing. It's in the background. Okay. It doesn't show though. How do I show? Okay, there it is. It's in the background. You can see the background. It's a hard to, I'm going to make this extremely big. I just don't understand. Why can't I just do everything is, okay, there it is. You can see my screen. Actually, what is it? Doesn't have a live thing. Okay, yes, you can see in the back there, it says hello. It says hello, welcome, I'm MES biggest fan. Anyway, that's actually my niece. So my niece actually wrote this. She wrote, hello, welcome, I'm MES biggest fan. Shame on you. And now it's because I showed her this thing. She said, she saw what shame on you. I think it was some song or something. And then it said, hey, do you know the quote from George Bush? Oh, that's shame on you. And she's like, who's George Bush? But anyways, I showed her this thing. So here's George. And then let me know the audio, if it's echoing or not. Let's play it. Okay, let's see here.
Shame on you.
Let's play normal speed.
It
Is there echo anymore? I figured out that echo before another guest. Okay, let's go right here.
There's an old saying in Tennessee, I know it's in Texas, probably in Tennessee, that says, fool me once, shame on you. It fooled me, we can't get fooled again.
Okay. All right, George Bush taking over the game. And then also, this was one of the funniest videos. This guy here, it's from Nilo Virgin said, fool me once, shame on you. Fool me twice, shame on me. Fool me 3 times. Okay, and he keeps going on. Let's see if this plays. Okay, this is just annoying. It's like everything it has to be an annoying thingy. Because I'll just play it on this thingy. Okay. Okay, and I have to play it on this. It's like just refresh. Just what is the issue? Using the Telegram web, just because I'm on a Mac. Telegram desktop isn't as good as the web. Okay, now it's gone. So it's like, what is going on here? Okay, anyways, guys, this live stream, half of it is going to be like just me troubleshooting, like, what in the world's going on. Okay, let's go back here. Okay, so now I can't see the thingy. There's no comments anymore. Okay, there it is. Okay, so where's the, oh, there's the comment. Oh, this is on the, okay. Let's play this. Okay, so now it doesn't work. Like, what planet am I on right now? Like, why doesn't things just work? Okay, so that doesn't work. So what I have to do is pull this out. And also, I just want to see how the streaming thing is working. Is everything's fine? Okay. Okay, that doesn't, I'm going to play the audio. Doesn't things just work? Okay, so that doesn't work. So what I have to do is, okay, so that's working fine. Okay, so that, okay, I'm going to go back here. There's, apologies for, okay, anyways, 29,000 tons. Thermite says, I think he's saying I'm getting on Hive at 9/11 anniversary. Yeah, definitely. Get on Hive. Again, Hive is like, you have to realize, I was trending first on Hive, my 9/11 playlist. Okay, you'll never have that anywhere on any other platform, ever. Like, and I had 9/11 like my playlist trending on Hive. Okay, that's not gonna happen on YouTube and so on. Especially get on it before all the Richard Gages and all that take over, because there are some disinfo agents on Hive. And even the Eric Dubé, I think he had an account like years ago. Even the Flat Earth Dave guys, like they know what they know. They're given the script on where to go. So they've been on that for a while. Okay, so I'm gonna go play this. I need to show that song. My goodness. Okay, I'll put it on here. Niece. Okay. So my niece made this poster. Okay, so this is the desktop one. It's not as good as the other one. Okay, so here's this one from 9/11 Versions. Okay, I gotta play it. Okay, just What is happening? Okay, this is me. Everything I do is SP is double speed. Okay, just normal. There's not even a button to click. Okay, let's play this.
Fool me once, shame on you. Fool me twice, shame on me. Fool me 3 times, it's twice as much shame on me. I cannot believe I allowed you to fool me again. Should definitely learned from the first time not to be fooled. Fool me 4 times, shame back on you. Actually, you are picking on a vulnerable man.
Alright, anyways, it gets pretty funny. Okay, and also my AC is working in the background. So can you guys hear that in the background? I'm gonna use that noise canceling thingy again. Let's see, where's that filters? Oh yeah, I have the noise gain. Okay, the noise is gone. Okay, that is gone there. Alright guys, so shame on everybody, shame on you. Okay, and Rudy Matrix in the house. Okay guys, we have a whole bunch of top fans are in the house. Okay, let's go. And then number 1 is 29,000 tons. Never mind. All right. And now, okay. So at least this thing's working cool. Okay. At least this one is fine. Okay. So we'll do that then. I'll whenever there's an issue, I'll just pop up that. Okay. I'm gonna just go back here then. All right. So let's go back here. Okay. And yeah. So now before I go further, I'm gonna go over also this kind of Gmail stuff. Okay, so here's an email. Okay, and this is another thing. My pet peeve is like, I don't understand. When I send email, why do people forward? Like, what is this? I sent an email, and now there's like 4 different chains on this email chain. It's like is it a Yahoo thing? I found it Yahoo. That's John Hutchin. Like all of them are just like a reply. Just reply normally. Like here's the original email, July 28th. Now it's like there's 4 different email chains. Like what planet am I on? Because I know they can reply. Because John's replying here. But why are you making, like, why is there, why, I sent this email, and now there's a reply chain everywhere. So, for example, you go, magnets in repulsion. So again, Gmail has a pretty good setup where it's all that, and now it's like, there's 4 different ones. This is the original one. No, actually, yeah, this admin machine, this is the original one right here. Actually, no, this is not the original. Where's the original? Here's the original. Nobody even replied to my original. Yeah, so the original is here. And now, because John sent this one as a forwarded email, like why are you forwarding? Now there's an email chain here, and then John sent another one after I replied to that one. So I replied here. Where did I reply? So I think I replied here. Oh yeah, then I replied here. And it's like the forwarding always makes these like giant long posts. Like where is anything? Anyways, that's me yelling at the world. Don't hear it. Okay, don't hear what? No background noise. Oh yeah, because the thing is on. Yeah, the background noise has it here. Yeah, that's because they kept the filter settings from last time. And how's the audio of that? Did it do echo? Was there an echo in that guy's speech? So I think the echo was from Microsoft Teams when I was sharing sound. So I got to figure that out. Anyways, so now the next setup is. All right, so and I'm gonna reply to this email just because okay, so I'll show you what I wrote, just the main email. So I said, hi, Chris AL, because Chris Berger, he's the one who funded the operation. So I said, I've just published the Atwood machine experiment for the videos and for video for the magnets and repulsion drop test. This one right here. Again, watch this video, absolutely mind-boggling. Which I think, again, I just need to double check by doing it at higher heights and so on, but I think it's a real deal. Because I can literally feel it when it goes down, it just feels slower. And even the bounce, bounces like weaker. So there's magnets in repulsion, the center is going down slower. All right, and let's go right here. Anyways, so I definitely think this shows that magnets and repulsion fall slower in gravity as per Boyd Bushman's claims. I'll repeat the experiment at a higher height, like my balcony, as well as performing 10 plus drop tests at one time to confirm repeatability. Chris, thanks again for the Atwood machine. So you paid for that $100, $100+. He also helped fund the Tesla coil. So again, he's got a lot of money thrown around. So Laurie, perhaps you can describe as Laurie Gardy for the fractal moment. Perhaps you can describe the drop test via the magnetic isopotential lines with the Earth's magnetic field, as well as modeling the previous magnet and repulsion through a cover test that Paul Mueller performed. Let me know if you have any feedback, as well as if you want to re-upload the experiment on your own channel, and we'll send it your way, and so on. Yeah, so it's like, okay, I sent it. It's pretty straightforward. And now let's see. Laurie sent this one here. Here's a ChatGPT conversation I had on the subject. Let me know if you can see this conversation. It seems surprised at the extent of the time difference of the falling between magnets and attraction or repulsion. and she sent this thingy, basically saying initially said that ChatGPT thought that it wouldn't be much of a difference. So said the difference should be more subtle than what we're seeing. It also gives a few suggestions of why this might be. Yeah, but the thing is, it's like no one's ever done this. Okay, like publicly besides Paul Mueller that I know about that has a video of it, and it goes down like literally half the speed. So again, and ChatGPT said that it would be subtle. So it's like okay, that's it. So you can ask it right here. Here's ChatGPT's response, and she says. If I take two magnets and glue them together in repulsion and then drop them through a copper tube, will they fall faster, slower, or at the same speed as the same magnets? This is a great question. Short answer: the magnets glued in repulsion will fall slightly slower through the copper tube than magnets stuck in attraction. Okay, so we got ChatGPT completely way off. So again, this is a quantitative like anomaly. So and that's a hi Lori. Thanks for the ChatGPT input. She actually put the different numbers. It's a very interesting stuff. Note that the time difference is much larger for the stronger N52 magnets, which drop in 37 seconds in attraction, but 72 seconds in repulsion. So here's 37 and 72. Also note the super high Gauss readings at the center of the magnets in repulsion. And lastly, here are some cathode ray tubes of the magnetic field in attraction versus repulsion. Note how tightly compact the repulsion field is. Anyways, I'm showing more info, but it's like, does anyone, am I like talking to nobody? Do NN and SS fall same speed? I think there should be a slight difference, but I haven't tested those. Yeah, and the Atwood machine results suggest that magnets repulsion interact directly with gravity itself. So again, it's like they're ignoring part of the gravity. Chris Berkshire says, then he replies, yeah, Chris Berkshire, yeah, it's like, he sold me this before. He has a good idea, but it's like the thing I'm trying to do is like literally prove that it's true first, and then we can go here. So Chris Berkshire says, Matthew, I recommend perfecting the Atwood machine experiment with attracting and opposing magnets that anyone could easily replicate. You could even make them your own kit and figure out how to sell it to high school and college students so they can prove their physics professors wrong. You could have the magnet machine to exact weight so their fall times are slower and could also coincide with an exact integer seconds number. The machine could act like a gravimeter, showing the minute difference to gravity over the Earth's surface. Did you try and then this is a gravimeter. I gotta figure. I was gonna call this stream. What is a gravimeter? So we'll go over this later. I just want to go over it because it's separate. Minute difference of gravity over the Earth's surface. Did you try a small copper bolt to hold the magnets together? I was thinking. Someone said a zip tie because I want the lightest thing. I don't want anything heavy. This pipe clamp comes with a small copper bolt. I would gladly offer you my 3D CAD drafting services for free of charge for the parts and the kits components that you would need to have manufactured. So yes, this one I'll definitely I think yeah I'll take him up on this. He says you could sell 10,000 of these kits for $100 when a kit would cost $10. I have a few contacts in China that could make the parts very low cost if you're interested. Again, that's very epic stuff. So that's where Lori says, can you? So again, she's getting confused. We're talking about the magnets falling against gravity. To all, can someone please explain to me how this proves physics wrong? That it is true that magnets slow down when dropped through a copper tube. This is because electromagnetic induction, which creates eddy currents. Anyways, just mainstream mumbo jumbo. But again, she's ignoring everything I said. It's like when people have preconceived ideas, it's like, and then they ignore what's actually being written on there. Anyways, however, the field around two magnets attached together under attraction is drastically different from the field around two magnets attached together under repulsion. It's likely the cause of the time difference. Again, we're talking different things. I'm against gravity. If they fall at the same rate, I would be surprised. Also, dropping two magnets in a gravitational field is not the same as dropping them through a copper tube. Yes, that's the point. It's like there are no eddy currents when dropping magnets in a gravitational field. I can't just stop talking. It's like, sorry, Lori, but you're talking nonsense. And then John Hudson, brilliant Matthew. The old iPad had a gravimeter app for the DESI papers. They wrote about particles, directions. I think the force is very interactive. Teaspoon of neutrons is very heavy. I don't think the force of natures are separated. They LOL interact. Boyd Bushman was right. Idea great on building the great idea. Matthew, thanks for remember what a cubic mile of sunlight weight. I read this long ago. That's papers. All right. I'm gonna reply here, then go back to the thing. This is yeah, hi, yeah, I'll say the DESI papers. Yeah. So, John, the interesting stuff, something about the Desi papers. Again, I need to. Yeah, he kept talking about the Desi papers. It's some like advanced science stuff he's doing. Anyways, I'm gonna go right here. What's your opinion on the accelerometer showing no downwards force? The accelerometer on what? Like what you just who's saying stuff? Accelerometer showing no downwards force. It's similar to induction. It's like if you have a magnet near near a copper tube, nothing happens. But if you move it, it's the motion that matters. Thanks for the offer. Definitely a great idea, which I will take it. Which I will take it up once I confirm that the Atwood machine runs are true. Will do. Yeah, so I will do the drop test at a higher height. I'll do the drop test at a higher height and repeat them more times. I want to stick with the glue for these confirmation experiments to minimize all non-magnetic weight. Lori, I think you are yeah. Okay, Lori, we are referring to the magnets Atwood machine drop test. Not the upper tube drop test. When you drop an accelerometer, it gives a reading of 0 movement when it's in free fall. That's what's supposed to happen. Accelerometer, it's not. Yeah, when you drop an accelerometer, it gives a reading of yeah. So that's interesting. It's free fall. So again, we'll have to ask that. And this is from Iraq, but both of you are sure that our fathers fought against each other in Iraq, Iran. Yeah, they definitely. They definitely did. My dad was actually like a shrapnel. Like apparently, yeah, he was sent to I don't know, Kuwait or something. I don't know where he was. He was in the army, and then apparently it was like friendly fire. Like the general accidentally told his guys to shoot a missile or rocket at a location that they thought it was the enemy's one, but it was actually where my dad was, and it blew up. And then like shrapnel hit his leg, then he had to basically get discharged from the army, and then we ran away. uh, ran away to ran away to the United Nations refugee camp in Turkey for like 3-4 years. Lived in tents, so it was pretty wild. And I got here in Canada when I was like 6 years old. Okay, so Lori, we're referring to the Atwood machine drop test, not the cupboard drop tests. In my first email, I asked you you can provide yeah, an explanation, an illustration of both tests using the ISO potential line. Okay, so the Atwood, I'll send the links again. I'm gonna go peek. Anyways, I want to do this. It's easier, and it registers normal force when sitting on the ground. Yeah, that's because yeah, the free fall thing. It's like it's similar. Yeah, but yeah, that's why it's similar when you're falling. Like if you're falling, you don't feel anything, unless you're being accelerated relative to something. So that's could be it. But anyways, this is it's like it's like I'm telling people things here. Okay, I'm gonna just yeah. So there's that. I'll send it here. Okay. We're Atwood drop test. Okay, I'll go Atwood. Referring to the Atwood machine drop test. Atwood, yeah. Yeah. Yeah, okay, and then we'll go Action Lab. Let's show you what Action Lab did. Oh my goodness, YouTube. Boyd Bushman. So now the first thing that shows up is Boyd Bushman. It's literally Boyd Bushman Action Lab. Yeah, so it's like he's like the first one here. Magnets drop.
Hey everyone.
Okay, and then okay, I'm getting 1 second at the door. All right, we are back. Okay, so anyways, I'm gonna finish this out here. The first thing I'll ask you if you could provide an illustration of both sets using the magnetic isopotential lines. Um, the yeah, the copper tube tests are interesting in that they are the only publicly available the only publicly available demonstrations of magnets and repulsion. Yeah. Falling through a copper tube anywhere on the internet. I think I think the much bigger yeah, much slower drop times are very interesting and may yeah, and may open avenues in physics not previously yeah, not previously understood. Okay, if the for the dropping in gravity, according to mainstream physics, they should fall at the same rate as this mainstream Action Lab would be. Yeah. Yeah, points out in his bogus debunking video. The Atwood machine allows for lower acceleration rates. Thus, more can be obtained. All right. And I'll play that video in, soon here. So anyways, I'll read this out. Hi all, thanks John. Interesting about the density papers. Chris, thanks for offer. Definitely a great idea, which I'll take up once I confirm that Atwood machine results are true. I'll do the drop tests at a higher height and repeat them more times. I want to stick with the glue for these confirmation experiments to minimize all non-magnetic weight first. Lori, we were referring to Atwood machine drop test, not the copper tubes drop test. In my first email, I asked you if you could provide an illustration of both tests using magnetic isopotential lines. The copper tube test, the magnetic isopotential lines, using Earth's magnetic field for the drop test for the Atwood machine. The copper tube tests are interesting that they are the only publicly available demonstrations of magnets and repulsion falling through a copper tube anywhere on the internet. I think the much slower times are very interesting and may open up avenues in physics not previously understood. And even quantitatively, that, yeah, I'll just say, and may even quantitatively disprove mainstream physics. But I will need to work out the numbers first. Yeah, the key part is quantitatively, okay? This was a quantitatively. But we're not even talking about that. For the magnets dropping gravity, according to mainstream physics, they should fall at the same rate as this mainstream action lab points out in his bogus debunking video. The Edwin machine allows for slower acceleration rates, thus more precise measurements can be obtained. And my Atwood experiments appear to confirm that you can appear to demonstrate that magnets and repulsion do fall slower. But again, I will confirm this with higher heights. Okay, cheers. All right, there's my email to a bunch of peeps that just don't grasp what in the world's what in the world I'm talking about. It's like ad serving protection from iron. Okay, some Google begin using. Okay, this is as previously announced. Google will begin using machine learning to estimate the age of signed-in users in the United States. Over the next few weeks, we'll begin to roll out this update to a small set of users in the U.S. to help us further protect young people as they use Google products. Okay, so they're gonna literally use AI, machine learning, for our publisher ad products. When our machine learning model flags a Google signed-in user as likely under 18, they'll be provided additional ad safeguards. This includes disabling ad personalization, disallowing sensitive creative categories from serving. Interesting. So we got AI taking over. All right. Let's see here. In a register normal force. This was a good question. Here. The Zoom with Fetzer lesson has been uploaded. Yeah, I heard about that. I see your message. Yeah, that one. My Mac. I tried to share a screen, but I couldn't share it. Because it's like I had to restart the Zoom. Because with Mac, anything you have to do, like if you want to share a screen, you need to give permission, and then you need to restart the app. It's like they turn everything into like an app. You don't. It's not like a program on PC where you can just run it. Okay, so this is yeah, this guy here. You can tell when every time he mentions the word Judy Wood, it's like he's literally tripping. And is that Gene or something? Who's this guy? No, that's someone else. Yeah. So Susan is very interesting. She's definitely in on this whole scam. And it's like near the end, they were literally trying to go on before I can like go on the call. Did they cut me out? No. Let's see where I am. I think I was right after this guy. They didn't show my. I showed my face, right?
He used nukes.
And this guy is like, his like chin is just like melting. My goodness. Okay, okay, the transcript's up at least. So we'll go here. Just want to see where I was at. Let's say share. Okay, this one here is me.
Greatly appreciated that.
No, this guy here. No, it was after this one, I think. Share screen. Okay, that's Gene. Gene is very interesting. Okay, going back again. See, I can share my screen and get 210.
Go ahead, Matthew.
Yeah, well, it's 1 minute. Basically, if I can share my screen quickly, because he keeps talking. And how come this show my face? Because they didn't even show my face. That's interesting. Nukes and high heat, but the evidence shows there was very little heat. So what are your God, how do I share with sound? Yeah, see, it's like the Mac thing is it's always an issue. I need to find where this is. Okay, so I'm not sure. I'm using a new computer, so I need to figure out which one I'm sharing.
I'm gonna defer that.
Okay, the question is, well, it's hard to say. He says I got to defer that. It's like, why is there? There's very little heat. So basically, there's very.
So then they only give me 1 minute, so I'm like, I might as well just go all out. Let's see this.
Little heat. There's people walking on the parts where you're saying it's 1400 degrees.
Listen,
And the toaster
listen,
cars.
There's people walking on. He's literally saying the ground is like 1400 degrees.
The toaster cars were before the towers fell.
Yeah, and also the toaster cars before the towers fell. He was saying that the radiation caused them or something from the nuclear bomb. He's literally talking about a nuclear bomb in Manhattan. Like, what is this guy on?
Thoughts about that before any of this mystical nukes hit it, and also to elaborate on what Ryan was saying, was basically Judy Wood was saying that she gives evidence of cold directed energy weapon similar to the Hutchison effect, which she actually said you threatened her. Once she got on the Hutchison effect angle, and you said don't include that in your book, or else you know what happens to people like that. They usually end up dead, and so on. So and that along with your dealings with Ace Baker faking his death on live radio.
I mentioned live radio. I always mention.
I'm just wanted to raise it up for those who don't know.
God, are you using this for a last minute smear? Susan,
Hey, give me 1 minute, and I can't share my screen. But anyways, so the low heat. What's your thoughts on the low heat?
Pointless.
What's your thoughts on the low heat? No, Jim,
It
can
was
you?
fast underground heat until mid-December,
Yeah,
and it's
but there's low heat.
inexplicable
There's
by
people
any
walking
other
on it.
hypothesis.
There's thousands of people.
Susan, please end it.
Yeah.
Thank you.
And
Once again.
then he literally runs away, and they kept dragging it on. I had my hand up for like 20 minutes, and then they kept like skipping me. Then they had a new guy cut in, and Susan cuts in. The host cuts in, and then they're like, "Oh, we're about to close it." So then I literally had to talk in ahead of it. Like I had to cut in. They were gonna kick me out.
Very much. I
Okay.
appreciate
I think you got it. And that was enough of that.
All right, so she muted me, and then they kicked me out. But anyways, well, no, I didn't get kicked out, but she muted me there, and then because usually once I mute, I just go on the down low for a while, so that they don't kick me out forever. They deleted my question. Interesting. Oh, they actually deleted your question out? No way. Now versions they deleted his question about why he the Smith Mundak. Are you sure? I don't think they're that. No, you're right here, Smith Mundak. No, they didn't delete the question. 14053.
Of the 1948 Smith-Mundt Act, Obama repealed it in 2012, which then permitted propaganda to be disseminated in broadcasting. Disseminating information then no longer said that it had to be credible. I've seen on many discussions, forums, platforms, and everywhere where people talk about the Smith-Mundt Act being in effect, but prior to 2012, before it was repealed, you and Richard Gage held your 9/11 hearings in Vancouver and Toronto, Canada. So the suggestion has been made that you and Richard Gage could have been charged with treason for disseminating propaganda, especially taking into consideration that the thermite, molten metal, and nukes have never been filed in an RFC to NIST, or this claimed explosive evidence has ever been taken to court. So could you please address the reasons for holding your 9/11 hearings in Canada whilst the Smith-Mundt Act was still in play? And when will you file your explosive nuke evidence to NIST or take it to court?
Come on. This is a serious group. Look, I just organized it in Vancouver. It's a beautiful location. And we had the hearings there. I don't think at the time I was even aware of the Smith-Mundt Act, much less the Smith-Mundt Modernization Act, which hadn't been passed yet, just in time for Sandy Hook. That was really to give cover to the crisis actors who'd bring a Sandy Hook and a host of others. But I think you're making an extraordinarily contrived argument here. I don't find this a serious piece of exchange here. Thank you. Just ridiculous, in my opinion.
Last question then.
I have published my work. I have widely announced it. I've been flown around the world to give lectures on 9/11, and I'm not going to stop.
I've got another question. I don't want to hear how important you are in the 9/11 space, because a lot of people have pointed out your shortcomings, especially with.
Well, talk to my wife. Talk to my wife. She'll give you an expand.
All right.
Your next question, you have 1 minute left.
Okay, so I would like you to then explain with your nuke theory the lack of seismic readings, the undamaged bathtub, and the anomalies with buildings 3, 4, 5, and 6 that cannot be explained due to thermal or kinetic mechanisms. Also taking into account the strange anomalies with 1,400 cars that were basically spontaneously combusting blocks away where the engines melted away and all of that kind of aspects. And then also the missing firemen who just disappeared, but their locator alarms were still found.
Listen, I've already suggested you want to go deeper on the use of nukes. I think Joe Olson would be a great guest for you to have. But I mean, you're elaborating a whole list of
Well, you
old-
have my email and my exchanges with Joe Olson on file, and it's also on my Substack, and
Okay,
people
good,
have been
good,
reading that.
good,
So
good,
I haven't got
good,
time
good,
for him,
good,
but
good.
I haven't got time for you either because I think you're a disinfo agent.
God, you know, this is fascinating. I've probably done more to expose government complicity in JFK, 9/11, Wellstone, Sandy Hook, Boston
Cover
bomb,
up, you mean?
even
You've
the moon
covered it
landing.
up.
But
You're a
anyone
liar.
who
Yeah.
covered it up, I'm exposing it again and again.
Covered
And
it
I
up.
published my work. In fact, it's so explosive, the government has to ban it. 6 of my books have
You
been
don't
banned
deal with the evidence. You call it theory.
about scientific issues, and you're acting like little children calling names.
You're the
That's
one.
pretty disgusting.
You're the one
I was
throwing
really-
insults.
I
though.
was
You're the
really
one that's
happy
being
to
childish
come
at
here
the
for
moment. We're talking
9/11,
about
not
facts
to
that
hear,
you
not
can't
to hear
explain.
pablum, childish accusation from
Oh,
incompetent
is talking about the
individuals.
seismic evidence childish, Mr. Fetzer?
Susan,
Maybe you should talk about the seismic evidence.
Susan, these guys are way off base.
Yeah, explosives have seismic signals. Liar.
All right, I think.
I clicked the wrong mute.
Okay, and
Sorry.
then they started muted everyone. Yeah, that was Ryan as well. Ryan from Field Interference, and yeah, so he actually has contact. He can contact Dr. Judy Wood. I told him, yo, get on the show. So he's gonna try his best to try to get Dr. Judy Wood on the show. So to maybe do a presentation and so on. So yeah, so again, I was surprised they let us call him out for that long, especially Ryan and Norman. And this guy's melting, so it's really weird. So you can go Fetzer right here. Actually, I should go leave this one here. I'm gonna go. I'm gonna keep that one open for. I'll put this right here just so that. Okay, this is live stream. Put it on the other side. So so what happens here? Yeah. So if I go click here, I'm gonna click Fetzer. So if we click here, Fetzer. Face. So his face is actually melting. So, clip from German Warfare interview with 9/11 disinfo agent Jim Fetzer. His face literally starts melting. Yeah, molecularly dissociating as he slenders Judy Wood, and you can see his face there. It's like, oh man. But yeah, I don't know why the quality is so low there, but yeah. Anyways, I'm gonna get that nuked right here. Yeah, this is okay. So I'm gonna put this. Yes, I'll keep that one here. This is the Telegram. So I'll put all the stuff here. So there's that. Gravimeter. Okay, so anyways, this is the thing he wants to get a coppered one. Someone else gave me a good idea, actually, to use a zip tie. So I might use a zip tie because again, the magnets are extremely strong. I'm using N52, like ridiculous strong magnets. They blew up literally right after. Okay. Anyways. Okay, but yeah, I do want to show this. This is the Action Lab. So if you guys haven't seen, my magnets. Yeah. So yeah, again, the Boy Bushman one. We'll play some of this, guys. But I'm gonna go. I need to go wash them. But before I do that, I just want to get close-up stuff here. So anyways, so I sent a bunch of stuff to these peeps. Hopefully they grasp it. Okay, this is what I wanted to get here because they sent an email with the document. This is a Fetzer. Oh no, that's just a text. Oh, they said they used the AI to get the transcript and so on. Okay, so because he has some good points in his presentation, but again, it's like mixed with a bunch of lies and nonsense, like the nose out mumbo jumbo. It's like just straight up nonsense. Okay. Alright guys, anyways, what is the next setup? I'm gonna play, yeah, so I'm gonna go here. But before that, yeah, so we have Fetzer, I think there's something else, Fetzer Hutt, I think, something like that. He looks like the Jabba the Hutt, Jabba. Okay, so what is Jabba the Hutt? Let's go, Jabba the Hutt, I think it's like Jabba the Hutt. Is that what it is? He looks a pizza. Looks like the pizza guy. Here's Jabba the Hutt. This is like Fetzer, but he's also the pizza guy. Oh, Pizza the Hutt from Spaceballs. Pizza the Hutt. No, Pizza Spaceballs. Is that what it is? Where's okay? This guy here. Okay. That's Spencer. But anyways, stop fat shaming, Mr. PhD expert liar. It's like, yeah. So that was Ryan. So Ryan, he's gonna try his best to try to get Dr. Judy Wood on the show. So that'll be pretty epic. Anyways, guys, we have 70 guys in here. Let's see what else we had in the show. Oh yeah. Also, why magnets attract or detract. But I'm gonna go right here quickly, and I'm gonna go to the washroom and I'll be back. So I'm gonna play. While we're at it, I'm just gonna play that full thingy here. I'm gonna go watch it. I'll be back. It's this song right here.
Fool me once, shame on you. Fool me twice, shame on me. Fool me 3 times, it's twice as much shame on me. I cannot believe I allowed you to fool me again. She definitely learned from the first time not to be fooled. Fool me 4 times, shame back on you. Actually, you are picking on a vulnerable man. Something has obviously gone wrong with me. This is like bullying the kid in a wheelchair at primary school. It's like, bully the fat kid, bully the kid with the limp. 4 times you're gonna fool me? Unbelievable. Fool me 5 times, shame on me again. I mean, I'm vulnerable, but at some point you have to take some personal responsibility for crying out loud. I've got 12 of these, they're good for 8. Fool me 6 times. Fool me 6 times, 6 times a fool. And I have lured you into my trap. Pretending to be a fool 6 consecutive times to give you a false sense of security, only to flip it. And now you are the fool. And you have the shame. Fool me 7 times, you saw through my trick. But there's no shame, because I'm getting fooled by the best. Fool me 8 times, and this is no longer a fooling, this is a systematic cruelty. And rather than allocating shame or even looking at you as an individual, I'd like you to unpack the nature of your fooling, remove the fool.
Anyways, that's enough of this fooling. This is too funny. Alright, so fool me once, guys. Shame on you. If you fool me twice, you won't. Okay, anyways, see what else we have in this. Again, this is again, these Wednesday streams are mainly me to unpack my mind and force it to learn stuff. Alright, so I'm gonna go with this guy here just to show you. So the magnets in a drop test. This is a gatekeeper, 4.98 million views. So he's again, it's like gatekeeper. He has good experiments, but then obviously anything like actually important, he has to cover up. So let's play what he says here.
Today I'm going to be dropping magnets and seeing if they drop as fast as, the same, or slower than regular objects. As you know, Earth is magnetic due to the convection of molten iron in the outer liquid core. So because the Earth is a magnet, does that mean if we drop a magnet on Earth, it will be attracted to it, and technically it should fall faster than a non-magnetic object? So I'm going to be testing this out along with another interesting theory proposed by Boyd Bushman. Boyd Bushman was a Lockheed Martin inventor, has a lot of patents in his name, a really cool engineer, but he also had some really weird theories. One of the experiments that he said he did is he got 2 magnets and forced them together. So he took 2 of the north poles of the magnet and forced them together, and then he dropped them off a building. And he claimed that they always fell slower than something that didn't have magnets inside of them. So I'm going to be doing that experiment also today in a little more controlled manner inside of a vacuum chamber so we can negate the influence of air, and then drop the magnets and see if they actually fall faster when we force the 2 like poles together. So first let's go ahead and test if a magnet drops faster than a regular object because the Earth is magnetic. Okay, so here's my setup. I have my vacuum pump going to my vacuum tube here. Also at the top here I've drawn
So here's there's one thing that's first a point. So he doesn't want any air resistance. Yeah, but the thing is, the Boyd Bushman one dropped it in air. So even it, so even if it doesn't drop in a vacuum, but it drops in an air. So then the question is, well, is the air conductive somehow? Is that causing it somehow? So it's like, just why are you using a vacuum? And why are you dropping such a small height? Anyways.
On a red line.
So it's like to avoid air resistance, yeah, but the thing at the same time, it's not the same claim.
This is where I'm going to be starting all my start times and then ending when it hits the bottom.
And then I have two identical balls here. One of these is a magnet and one is not. Okay, turn on the vacuum pump.
So he's doing the magnet one first. But again, this is like, with gravity, it's super fast. So it's like, well, you need to extremely precise setup, or just use an atwood machine.
Okay, 3, 2, 1. 3, 2, 1.
Now let's watch them both fall at exactly the same time at 1,000 frames per second. The frames are shown on the left side of each picture. And I measured that they both hit at exactly the
same time. Yeah, but notice with 0.334, like the atwood machine, that's the difference between the actual thing. So like the time that it takes to drop here is actually the difference that I was able to obtain.
Same time, 0.334 seconds.
So it's like, so again, this is like overly complicated on purpose, I think, because it's again the disinfo agent, etc. The gatekeeping, the usual setup as always.
Our error limits, we got the same time whether
because a 5 million subscriber YouTube channel is not going to say magnets and repulsion debunk gravity, debunk mainstream physics.
It was a magnet or a regular steel ball falling. So why doesn't a magnet fall faster to the Earth even though the Earth is a magnet? The first reason why this doesn't happen is the magnetic field of Earth is actually really weak. The magnetic field is only around 0.25 Gauss, whereas a simple refrigerator magnet is around 100 Gauss. But even if the magnetic field were stronger, it still wouldn't attract.
So what was that?
Refrigerator magnet 0.25 Gauss. Is only around 0.25 Gauss.
Also 0.25 Gauss, and then the refrigerator is 100 Gauss. Yes, that's way
Whereas a simple refrigerator magnet is around 100 Gauss. But even
okay, but I don't want to get copyright because the music's there. But anyways, let's see what he says here.
If the magnetic field were stronger, it still wouldn't attract it to the Earth. That's because the magnetic field that we're dropping it through is a uniform magnetic field. For example, right here I can mimic the magnetic field of the Earth by putting two strong neodymium magnets with their opposite.
Okay, so he has opposite poles like that. Okay, so
opposite poles facing each other. You can see that when I put this third magnet in between here, it aligns with the magnetic poles. But it definitely doesn't fall faster towards the ground because there's no attraction towards the ground.
Yeah, but you should put one magnet so that just to see how much it rolls. And also because the friction there is high too, so it's
attracted to the magnets on both ends.
But the question is, does it but why is he having two magnets together? I don't understand what he's doing. Anyways, let's go back here. So here's the setup that I really don't like what he did. This guy is like as if Wikipedia was a person, yeah. But he had some good experiments. I shared one of his experiments which I like.
Together.
So here's what
the two like poles are facing each other.
So here's what he did to get the magnets together. It's like it's again, you're adding extra weight. That's one thing, but also it's only dropping it from like a little under a meter.
If I put a lot of force on it, I can force the two magnets together. So now the two like poles are facing each other.
Okay, so they're not even stuck together. There's literally a gap. So like the strongest part of the magnet is not even together. Okay, the strongest is like literally right at the magnet. The magnetic strength drops out quick, and then he just puts a pin there.
Got them held in place with my drill bit here, which I drilled in, and then I'm going to cut it off on the edges.
So he has a gap there, and he just cuts it off.
Okay, so I've got that filed off just fine. Now I'm going to cut it right here.
Yeah, so now he has basically plastic with a metal bit, and look how far apart they are. It's just like two magnets just beside each other. The repulsion isn't doing that much.
Okay, here's our final product.
And this is broken too. Why is this magnet broken? What is he doing? He has a broken magnet in there.
2, 1. Okay, now put the attractive ends towards each other.
But,
so instead of just
but he has a broken magnet. Why does he have a broken magnet and he's not even mentioning that?
Comparing it to a regular object, normal object.
So anyways,
attracted to each other.
Yeah, so he has a broken magnet there. Why is it broken? What's he doing with his life? And this guy's got 5 million subscribers and he can't even make a proper experiment. Anyways, and here's the drop test.
And I get that they hit the ground at almost.
And it's like, but you're dropping so shortly. Like, what are you doing? I'll explain it. I'll see the real time. Here's the real time speed.
2, 1.
So look how long that's like 0.3 seconds, so under a
Let's look
second.
at them both dropping exactly
You're not,
together.
you're not gonna get anything. Just the difference of him pulling it could affect it.
My start time is measured from when the plunger end of the syringe passes the red line, and the end time is when it hits the bottom. And I get that they hit the ground
They don't hit the ground exactly the same.
at
Anyways.
almost
exactly. Okay.
back at the same time within 1/1000th of a second.
So although Boyd Bushman claimed that if you push two magnets...
No, not claimed. He literally did it. Basically he dropped it and it fell down slower. And he has like a paper that says it. I don't know where he got that from. But anyways, that's he's a Boyd and he's a Lockheed Martin engineer.
Together, they'll drop slower.
And now he's putting it on weigh scale. Yeah, but it's like these are separate things.
So I got a little nervous during this part.
6.
As a north together.
Before we go, I'd like to thank Blinkist for...
Anyways, and now he's like tiny magnets showing that there's no difference on the weight scale, but it's like he's trying the quickest way to debunk as opposed to trying to prove Boyd Bushman right. He's doing the opposite. He's trying his hardest to prove Boyd Bushman wrong as opposed to trying to prove him right. And that's the only way you can find if he's actually right or wrong. And that's where I literally I think Boyd Bushman is right. And you could even see here. So going back here, this is the Boyd Bushman replication, one by William Alec. I think he used to know John. So I think this guy actually met John Hudson. So I'm gonna play. Here's a drop test. So I'll do the real time one.
1, 2, 3.
Okay, go back here. The other guy drops from like under a meter. So in other words, 1, 2, and then that's it. Stop. It's like, yeah, these ones will probably have the same as well. But then you go a bit longer and it extends out. And you can see it in slow motion. Here's in slow motion. So this was the one. Again, this is why I don't like just dropping it like that, because this needs to be much higher. And then it drops down. And look at the difference is so tiny. So if the difference is so tiny, every single thing you do will affect it. If you add a drill bit, that may affect it. If you add plastic around it, that may affect it. That's why I had the thin plastic there. He's doing his hardest to get his advertising part. Yeah, but again, he's a gatekeeper. It's all part of the setup here. So like the Atwood machine one, this one, the difference between these drop to 3.666. It's interesting how it goes 666 and 4.1 seconds. This one is more. This is a bigger. The difference is more than the entire drop test length that this guy dropped it. So you go back here. Where's the drop test right here? Actually, what is he doing with these clocks there? Just get a normal time. So I'll show you what I mean. So I'm back here. So look at this is a non-magnetic drop test, but
3, 2, 1.
Now let's watch them both fall at exactly the same time at 1,000 frames per second. The frames are shown on the left side of each picture. And I measured that they both hit at exactly the same time.
Yeah, so here, 0.334. Okay, he's getting 0.334. The difference between these experiments. This is like how you actually find stuff. Like, someone says extraordinary claim. I will try my best to prove it right because I want it to be real. Like he just doesn't want it to be real because he's a gatekeeper. Okay. Yeah, so I'll make it a little double speed. Here's again slowly. Okay, so this is going down. Yeah, so the difference right here, this is already hit at 3.66, and this one's still going. Yeah, so 4.1 now. But the thing is, even this big difference, I'm still not saying it's 100% certain, even though I think it is. But because I need to make it even higher, I want to make it at least over a second difference, and that's what dropping it with like 3-4 times higher. So I'm gonna drop this from my balcony, get a super long string, and if it goes down 2 or 3 seconds, over 1 second, then that's it. Irrefutable, and I definitely deserve my Nobel Prize. So where's my Nobel Prize? Nobel Prize for you. When do I get my jetpack? In a few months. So again, it's like, and I'll go another part where this guy's a gatekeeper. It's like, this is the thing. Whenever you do something, actually understand it inside and out. So you can gyro rise on its own, rising. So gyroscope. How does a gyroscope rise? Yeah, so how do gyroscopes lift themselves up? So this one here, it's like he did this. I'm pretty sure he got it from me. Like he probably saw my videos and he doesn't want to give me credit. So he says, how do gyroscopes lift themselves up? And and he doesn't know the reason.
Stable. It's still processing a little bit.
Top portion here spins.
Okay, where's the?
At that same rate forever. So why does the gyroscope eventually get lower and lower and lower and then fall off? The reason for that is because in order to
I'm gonna mute these. They put the music so they get copyright strike. That's literally why they put the music on. You know that if you ever see the big channels, they also have music in the background. It's literally it's part just for entertainment, but also part to copyright because auto gets picked up. So anyways, go back here. So this is like a very cool top. So this one is extremely heavy. I actually like this one. So the guy who made this actually messaged me and gave me this. Well, like I paid him directly because he's like the guy who actually made these messaged me. He liked my videos, my gyroscope videos. And he sent me this one. So I have that exact same one he has, and it's so heavy. It's pretty epic. Okay, so here it is. It's spinning, and it goes up. And let's try to see what his fake explanation is. And I'll show you why his explanation is. It's so fake, where it's like he's obviously a gatekeeper, because there is no explanation for this in the scientific literature at all. They don't even know this is real. Okay, let's go unmute.
So it gets completely upright again. So how can I actually prove that it's the friction resisting the turn?
Yeah, we know it is. Friction helps it rise. Yeah, so friction is probably one of the reasons why it goes up. But the thing is, that's not the reason it's supposed to go up.
That's causing it to rise up in the air. Well, if I try to just give it some resistance like this, I'm actually stopping the precession as well, so it's going to tip over. So I have to find a way to only slow down the spinning without stopping the facing downward like a top. Then it will actually point the other direction. Up. This is actually the same reason why a top rises, or when you friction of the spinning, it's going to eventually fall down. But if it can precess really easily, but only has friction of the spinning bearings, then it's going to actually rise up. This is actually the same reason why a top rises, or when you spin an egg, it rises up on its end. It's actually the friction against the table that's causing it to rise up. Now,
no, that's not the reason. I'll go back
none
here.
of what I've explained here is intuitive at all. And in fact, none of it is even explained when you learn about gyroscopes most of the time in physics classes. It's actually very difficult to get a gyroscope to actually do what you're taught it's going to do. And I want to say thanks to my friend David.
So yeah, the Dave guy, yeah, he's the one who messaged me.
For actually making this gyroscope and sending it to me. It's awesome.
This is the part where he gets it wrong. The friction for a spinning top is not the reason. It's not the same friction. This is just spin friction. It's the other one that has like the friction that they're saying that the mainstream says here. Spinning top wiki. The spinning top in wiki. Spinning top. It's like everything is just a spinning top. So the spinning top in Wikipedia, what they say is that it makes a torque with the ground, so you could go rise right here. Let's go center or friction. Okay, and then let's see here. Typically, the top will first wobble until friction torque between the tip and underlying surfaces forced to spin with the axis steady and upright, contrary to what is assumed. Long-standing scientific studies and easy experimentation reproducible by anyone show that reducing the friction increases the time needed to reach the stable state. Okay, anyways, where's the rising right here? Did they just remove the rising part? Friction. Okay, how do spinning tops rise? And the other part he's saying the friction with the ground. Okay, this how does spinning top work? So again, I'm trying to. Why is everything so hard? Spinning top physics. Rise and fall of spinning tops. I think this is the rise and fall of spinning tops. So he's getting confused with the friction of the ground because the friction of the ground, it's not to slow it down according to the mainstream, it's to make it rise. Okay, I absolutely hate the mainstream scientific thing. Generally, let him know that he's wrong. I'm serious. This counts as misinformation. Yeah, he's a straight up liar. I could email him. But why is there just not... This is a cross rod guy. This guy here, the rise and fall of spinning tops is actually the one part of the Veritasium debunking spinning top. Okay, spinning tops. They have to show this. I had the full... Okay, there's the guy. I'm pretty sure it's Rod Cross. This guy, keep his name in mind. I'm pretty sure this is the guy in the Veritasium videos. So here it is how they say it rises. And again, yeah, he's in this video with this guy here, trying to debunk Eric Laithwaite. So they're saying a spinning, when this spins right here, it makes a friction with this, causing a torque to make it rise. Okay, whereas this guy here is saying that the friction of the spin is causing it to rise. That's not the same as the spinning top one, but this disproves the spinning top one, because all it needs is just the lowering the friction, and it just goes up. So here is so he added friction there and just goes up faster.
So it seems that there are two effects that can happen with a gyroscope. You drop it and it starts processing, and it will either get lower and lower and lower and eventually fall over, or you let it go and it'll get higher and higher and higher and eventually become stable at the top.
And they also ignore that it's a zero inertia, like the precession inertia is very little. And okay, now yeah, so yeah, I should email him actually. Yeah, so you should email him. I'll give him an email. I'll put that on my thing here. So this one here, this is a Rod Cross. Again, these guys are literally just debunk gravity. That's why I say the G and the Freemason logo is gravity. That's why I want it to be. And they ignore, yeah, basically the gyro rising on its own disproves how these ones rise on its own, because they're pointing at little friction thingies at this egg that rises. They're saying that the friction here is hitting it, but the gyroscope has this stationary and it still goes up. So you can see how it rises is here, and then they have some elaborate reasoning for the angular momentum vector L points along the spin axis, rises slowly as the top rises, and they're saying rolling and other mumbo jumbos. But I want to put that right here. Okay, so I'm gonna put this. So I'll do an email. I'll email him there, just because this guy is disinfo clown. Let's go. I'll say here. Disinfo clowns. And again, that Rod Cross guy, and his name is Cross. Interesting. That's why I thought I just removed the. Oh, that's why. Okay, disinfo clowns. This and that. Absolute. Like it's just ridiculous how sad it is. Like, how do people just look at it? Anyways, let's go. Veritasium. Gravity. Anti-gravity. I'm pretty sure this guy is the same one who wrote this article, Rod Cross. Because this Rod Cross, I'm pretty sure that this guy here, this guy's like a big...
Force must be greater.
He's definitely a big Freemason. Yeah, Rod Cross, there it is. Rod Cross, there it is. There's the guy covering up this. And it's like, this cover up too, it's just so freaking sad. And going further, there's a message here on, I should do this and then go back into what magnets are and so on. Right here, I'm going to click on, let's say, precession. Okay, this one, yeah, Nick says, I was supposed to do it before. He says, thanks for continuing to explain this stuff. Okay, and now it's like, how do I make this bigger? I just don't understand. It's so hard to read on Telegram web. I absolutely am getting like frustrated with everything. Okay, so I'm going to put here. That's what I'm using. Telegram on Mac is just absolutely brutal. Precession on the chat. Okay, this guy. Yeah, so now you can actually read it, and you can make it bigger at any time. The other one, I don't know how to make it bigger. Just like make it bigger. Maybe there's a way to make it bigger. You can't make it bigger. My goodness, I'll probably have to ask Grok. So thanks for continuing to explain this stuff. It's always hard to fully wrap my head around, and it also seems so simple. It is so simple. It's like I'm being lazy here, but I wonder what AI says about your findings on gyroscopes and how you would respond. Have you ever gone down that road? I'm just listening back to your PhD on rotating bodies again. Went through a lot of it in the past, but still trying to grasp in a deeper and more natural way. I tried asking Grok and ChatGPT just for kicks, but I'm too tired to parse through in detail. Don't know if I have the question right. The responses seem like a muddled mess with a quick read, but I'm too lazy to figure out what they are saying really. Would it be curious to see you argue with an AI on the details? If you ever do, definitely show us. I know you explain this stuff in many awesome ways, and I'm still working through it, so you might not be interested in such an exploration because you've covered it so thoroughly already. Just kind of curious. all around and hungry for more debate between between what you are saying in the mainstream, so I can really keep the truth of what's wrong with the mainstream locked in my mind. Wish I could sit with you and ask a million questions until I really understand. Anyway, either way, thanks for pursuing this over the years. For whatever it's worth, here's the same question for Grok and ChatGPT. Let me know if the question is way off on what's intriguing you about gyroscopes. And I actually replied to him, and where's the replies? How do I just reply? Like every single thing he has to have a thing here. I replied later. I said, yeah, interesting. Yeah, I'll debate it with AI next Wednesday. I was supposed to last Wednesday. Since AI is trained on mainstream data, you have to ask it what it thinks will happen for each gyro experiment scenario rather than explain actual results, which it confuses rising with nutation and lack of precessional momentum with spin angular momentum. Anyways, so we're going to debate Grok right now. I'm going to go with Grok and I'll ask it, if I place a gyroscope with a peg to make it behave like a spinning top on a low friction floor, what will happen to the gyroscope? Will it precess then fall, or precess then rise before falling? Alright, when you place a low friction, its behavior depends on several factors. Precession, nutation, rising. If the gyroscope spins fast enough, it can exhibit a behavior where it rises to a more vertical orientation, known as a sleeping top. This happens because the rapid spin stabilizes the system, and any small tilt is corrected by the dynamics of angular momentum. Alright, so how does it rise, though? Wait, okay, falling. Okay, let's go back here. Notation. Okay, notation. Steady precession may exhibit notation wobbling, basically wobbling up and down. If the gyroscope spins fast enough, it can exhibit a behavior where, okay, so this is the key part, rises to a more vertical orientation. This happens because a rapid spin stabilizes the system, and any small tilt is corrected by dynamics, precess and gradually align closer to the vertical. Okay. Let's see here. You should email. Okay. What actually happens is the gyro rises completely each and every time when initial spin speed is fast enough. Yeah. Before then falling. Okay, it's like you're correct. Thank you for clarifying. Observe behavior when a gyroscope with a peg acting like a spinning top is spun. Dynamic stability and rising at higher spin speed. The angular momentum is large, which stabilizes. What is stabilized? Precession and any nutational wobble. Small oscillations interact in a way that reduces the tilt over time. It's a hallmark of spinning top. No, but the spinning top. The peg itself is not spinning like the spinning top. Yeah, it's not spinning like the gyro rotor. It is a the gyro looks like a spinning top, but the only thing spinning is the rotor, not the peg. The peg is not spinning. And only the rotor is gyro spinning with the peg acting as a fixed pivot. Modifies slightly as the peg serves a non-spinning contact with a low friction floor, while the rotor provides the angular momentum. Let's analyze. Initial precession rising as a sufficiently high motor speed. The gyroscope exhibits a rising motion to a near vertical. No, actual vertical. A large angular momentum, torque from gravity combined with the rotor spin. Yeah, I know it caused it the way, but the thing is, how is it doing this? It's characteristic of a gyroscope or spinning top with a high angular momentum. The spinning top peg doesn't affect this dynamic significantly as the angular. No, actual vertical. Actual vertical. Not near vertical. Literally goes vertical. Alright, not just near, when Why? Okay. Release from solid gravity where rising vertical when spin speed is sufficiently high that angular momentum stabilizes these. Must exceed a. Okay. All right. Once the spin aligns exactly with the vertical, the gyroscope enters a sleeping state where it spins without. Okay. Anyways. This is because the gravitational torque vanishes when the spin axis is working, but it doesn't. It's just describing it. It's not giving a reason. Anyways, this thing is a bit out there. Okay. Now the question I have is, okay, let's say you have placed. Okay, I'm gonna go. Actually, here, peak experiments. I have them all. I'm gonna go right here. Whoops. Experiments. Like this dealing with this AI doesn't even know what it's. Okay, I'm gonna go right here. Yeah, let's go right here. Okay, let's go to the Grok one right here. Actually, I think I have a better one. Okay, so this one here, I'm gonna get the notes on this one here. Or this one here. I'm gonna say the notes. Okay. Let's say I have a gyro right here. Okay. Okay, this is my gyro on an ice block. Okay, the peg is on the ice block. Again, the rotor is the only thing. It's spinning. What should happen to the center of mass since there are very little horizontal force friction? The ice block. Will the center of mass move or stay almost, yeah, stay near the initial? Okay, so here, based on the image in your description, it consists of a spinning rotor. The low friction surface ice block acts on nearly frictional surface, meaning horizontal resisting pegs are negligible. Initial behavior: when you release the gyro with a slight tilt, gravity exerts a torque on the ice block. The lack of significant horizontal allows the peg to slide or pivot freely in response, rather than being constrained. The peg may move more horizontally across because the low friction allows it to respond to the center of mass. However, does not move significantly on its own unless acted upon by external horizontal force. The precession itself is a rotational motion of the spin axis, not a translation of the center of mass. However, the peg slides due to the lack of friction. The entire gyroscope, including the center of mass, will shift if the peg slides slightly along with the peg's motion. Okay, so let's ignore the rising vertical. The extent of this movement depends on initial conditions. The peg could drift, causing the center mass to move away. Yeah, so what will happen to the center of mass? Only focus on this, not the rising. Okay, if the COM is stationary, that would mean the gyro, that would mean the ice block moves in a circle, since most of the mass is near the rotor. Is this correct? Okay, an ice block near. Okay, move freely. Ice block moving in a circle. If the COM were somehow constrained to stay stationary, ice block itself will need to move to allow the gyroscope to process, since most of the mass is near the rotor, which is offset. The peg should trace it would trace a circle into the relative. Yeah, for the ice block to move in a circle, while the COM stays fixed, the ice block will need to rotate or slide, compensating. However, this motion assumes ice block is free to move, which is it's unlikely unless it's frictionless. Ice block is free to move. Ice block is free to move as it is on a smooth steel surface. Okay. Like this thing, it doesn't even know what the center mass. Anyways, Grok is talking to like a robot. When it deals with things that are science stuff, we'll have to do a think one maybe. That's a think one. Now it's frozen. Okay, I'll do a think. Okay, stop putting ice block moving in a circle. Since most of the weight mass near it, which is offset, if the COM remains stationary relative to the ground, the ice block must move to accommodate this. The peg would trace a circular path on the block. All right, there it is. But actually, that doesn't happen at high spin speeds. Only at slow spin speeds. At high spin speeds, the gyro, the gyro COM moves around the ice block. Then at low spin speeds, the ice block moves around the gyro COM. Alright, there it is. There it is, now it's thinking. Now it's stuck. Alright, there it is. We got Grok tripping. So again, the thing I'm trying to elaborate on is this part here. This thing it's not supposed to happen. This little tiny thingy is not supposed to happen. And I should put a peak anti-gravity part 6. Let's go to part 6. I'll show you what is supposed to happen. Again, I want to stress this enough. The biggest one of the procession was the one that Eric Collector kept saying, but everybody just ignored him and got like covered up and so on. It's like nobody just. It's like is it too technical? It's just very simple. It's just procession. Okay, is it too technical for peeps? Like I don't understand. What is the issue? Okay, so going back to here. Yeah, going back into the debunking. Yeah, so it's this. Where's the debunking side? Yeah, this one here. This is the from Cambridge University. It's Cambridge University. It literally says this should happen. This is not me talking. This is Cambridge University saying that if you're on an ice block, this is what should happen. All right. It's like what more do you guys need? Cambridge University literally says this garbage. It says this is what should happen. Okay, it says this. The center mass should be around here, and then this ice block should move. There are no lateral forces. Center mass must stay about a fixed position. So again, we're dealing with. Let's put it here. This info nonsense. All right, so you guys know I am not supporting these a-holes. It's like literally this info nonsense. Okay, and why is there no background? Okay, so that's the simple nonsense. I will do a screenshot right here. All right, and I'll change this up, edit. Okay, so that is that. What is that? I just sent it and it just, why is it sending a new one? Okay, everything is just trash lately. Like just, I'm gonna go here. Like every single thing ever. It's like, yeah, this is the only downside. Okay, this one here, just put it here like that. Okay, so it should update it. I thought it did. Okay. Anyways, yeah, that is updated. All right, so that is done there. All right, so we have 33 minutes. That's a good number. Okay, I'll just exit. Just discard. My goodness. All right. And let's see what this guy says. Your opposition is fastening at high spin speed. The gyroscope center mass moves around the ice block, while at low spin speed, the ice block moves around the center mass. Let's break this down and explain why this happens. Accelerating the dynamics of the ice block. Negligible explanation at high. Your behavior moves in a circle. Ice block is relatively stationary or moves less. May rise towards a vertical. Alright, trace a larger. This slow procession goes to center mass. Yeah, so slow procession goes around slower. Physical intuition, the gyroscope peg traces a slow white circle on the ice block due to the ice block's inertia and the low friction. Alright, we got it. We got it tripping. Okay, leads to a larger radius at low spin speeds. And now they're saying that inertia itself. So they're literally saying the inertia's gone. Wait. The inertia's moving, but it's slower. Creating the impression that the ice blocks are. No, it does. Creating the impression that the ice block circles. It does circle it though. Amplifies the ice block's motion with less angular momentum to stabilize the gyroscope. Stabilize. Or some high spin rates around ice block as of a slow progression creates a wide circle path and a higher. Alright, we got this. Let's go. We got Gark. Sign-ups in the back. Bahath is in the front. Baha, you mean? Oh, it's Bath. Yeah, okay. Okay, Grok tripping. Tripping. Okay, yeah. Like, all right, we got Grok tripping. Anyways, that's it's just pretty obvious that it doesn't know what it's talking about. Well, it's just describing. It's describing things. It's not telling me. It's not debating or anything. It's just telling me, yeah, I'm right. Here's why it thinks it's right. Okay, so again, I can't stress enough. This is mind-boggling stuff. Yeah, so this is going around. The center mass is moving without any horizontal forces, according to debunking mainstream physics, and so on. All right, and then once the spin speed slows down, now it's moving. Now the ice block's moving, and there it is. I stopped it earlier. I could have made it done more. Just the one. Yeah, there it is. At slow spin speed, you'll see what happens. Anyways, so that is that. It's pretty irrefutable for me. Okay. Anyways, let's go to why magnets. Okay, now why do magnets attract and not and other stuff like that? Actually, before we even get that, we'll get that eventually. Maybe I have to change the title. But actually, we'll do that just because we did the title. So the question is, why do magnets attract and repel? And so on. I'm gonna go here. This thing is I can't stress enough, guys. We're in the matrix. This thing is epic. Okay. All right. Yeah, so I may have to do like videos why this debunks everything. I'll do shorter ones. I should like it's sort of the ones I'm doing for the experiments. But anyways, the Action Lab guy, even though he's a complete clown and he has a copyright on like freaking the video that I uploaded. It's just because it captures the music. But yeah, I said it's all right because I just use it. So this one here, the ping pong ball floats in a water vortex when inside a vacuum. And this one is pretty interesting. I'll mute it right here. This is from him.
So I have here a ping pong ball.
I put this. I thought it was pretty interesting. So ping pong ball floats in a water vortex when inside a vacuum. So if you spin this up, it goes down. So it goes down when you spin it in a vortex. But then if you put it in a vacuum chamber, it goes up. So now if it's down and you keep spinning and then take all the air out, it just goes up. So it goes up completely. All right. So I thought that was pretty fascinating. So anyways, yeah. So basically, yeah, he's a gatekeeper, but yeah, but he's still decent info. Similar to Veritasium. Veritasium literally did his PhD on fake science. Like actually. Anyways, going back. Okay. Anyways, that is that part. Let's see if there's any comments on the Threadcast again down there. Now let's see what else is in here. Oh, this has comments right there. Oh, that's that. Okay. I'm gonna see what else we had in here. I think I'll do the Bedini motor next week. This is a message right here. This is these Bedini ones. Joso. This is Joso. I'll say. I will go over the Bedini motor. AL next Wednesday's stream. We'll show your info. Yeah, we'll show okay, so I'll go over that next time. Yeah, so now the question is, well, we need to at least answer the question of why do magnets attract, repel, and so on. Actually, before we do that, so we have that was the one link. Real ball lightning. Well, this was John Hudson sent me. Real bowling. But before we get to that, I'm gonna go physics playlist MES.fm. playlist. Okay, so you go here. Okay, why do magnets attract? But first, I'm gonna see what YouTube says. Why do magnets attract? So because it was a pretty viral one. Okay, why do this one here 11 days ago? This is 271 a fundamental level. Why? Because this guy's asking why. Let's see what this guy says.
Click the link in the description to take.
How are these guys all getting sponsored by Brilliant? I want to get the sponsor. Be like, learn all about 9/11 on our Brilliant Brilliant course sponsored by Brilliant course by MES by yours truly. Yeah, so all these guys, every single one of these, like a million subscribers, are getting sponsored by Brilliant. Anyways, see what this guy.
Take advantage of a special offer for Arvin Ash viewers. You've seen this 1,000 times. Magnets pulling things, even with very large weights. It almost seems magical that this invisible force can be so powerful. Why do magnets attract? What is the mechanism? What's actually happening behind the scenes at the atomic and quantum level? We're going to keep asking why questions until we get to the ultimate answer. And that answer is way more fascinating than you might think, and it's probably something you've never seen before. That's coming up right now.
Okay, anyways, see what the actual reason is. What he says, spin up. Oh, now they're doing spin up stuff, spin down stuff.
It's not exactly like a spinning top, but it is a type of intrinsic angular momentum. Each electron doesn't just orbit randomly. Electrons' atoms are composed of positively charged, and we need to zoom all the way in, down to the atomic level. Magnets are made of atoms, and atoms are composed of positively charged nucleus surrounded by negatively charged electrons. These electrons are tiny charged particles that orbit the nucleus, kind of like planets orbiting a star. Well, not exactly, but we'll get into that later. For now, let's just visualize electrons orbiting the nucleus like planets around the sun for simplicity. The animation you see here is a decent mathematical approximation. Each electron doesn't just orbit randomly. Electrons have a quantum property called spin.
And also notice the music in the background. Again, it's just for copyright mumbo jumbos. They'll fix it up.
Spin is not easy to visualize because it is a quantum property.
So it's spin, but it doesn't actually spin, okay? That's what the mainstream says.
It's not exactly like a spinning top, but it is a type of intrinsic angular momentum that particles possess, even though they don't physically rotate. It's intrinsic, meaning it's a property that electrons have, similar to the way they have a negative charge.
All right, so we have charge, things unexplained, and then the spin, unexplained. It just has it.
Each spinning electron generates its own miniature.
So each spinning causes the magnetic field, all right? But it's not spinning. It's just called spin.
Magnetic field. The magnetic field lines represent the strength and direction of the force another magnetic material would feel in the vicinity of the magnet. Now, most materials have electrons spinning randomly in all sorts of directions, so their magnetic fields cancel each other out, resulting in no overall magnetism. But in certain materials like iron, cobalt, or nickel, something special happens. In these special materials, electrons tend to align their spins with each other.
All right. So according to mainstream, it's basically all these atoms are spinning. The electrons are spinning the same direction, but it's not actual spin. But we'll call it spin, and then that spin causes attraction. Yeah, we're getting a phone call. New Hampshire. What is this? Hello? Hello? Oh, who's this?
This is Nolan.
Oh no, I'm good. Okay. Good, we got spammer, some like promo colors. Anyways, okay, electrons align their spins, okay?
Quantum mechanical interaction.
So we have a spin aligning, except spin, it's not actually spinning. So this is like, I hate their non-explanations.
I'll explain what those interactions are in a minute. When electrons align their spins in this synchronized way, their tiny magnetic fields combine, becoming stronger and stronger. Large groups of aligned electrons create microscopic regions called magnetic domains, where all...
Alright, so when they all spin together, they create a bigger magnetic field, and the magnetic field is just, again, intrinsic property, and it's not actually spinning. So, so basically what's actually happening is, these are little ether gyros actually spinning the ether, and then the more they spin aligned, the more the ether spins. That's my view.
Electron spins point in the same direction, creating a strong local magnetic field. Initially, these domains themselves are randomly oriented, canceling each other out at large scales. So the material overall is not magnetic. But when you magnetize a piece of iron by exposing it to another magnet or electric current, you force most of these domains to align in the same direction, turning the material now into a magnet. So that's how we create a magnet. Okay, but we still haven't answered the big question. Why exactly do magnets attract each other? The standard classical explanation, which you've probably heard before, is this. Magnets interact through their magnetic fields. These fields are like invisible patterns or lines coming out of the North Pole and going into the South Pole. You can even...
Again, the isopotential lines is the better one, because these field strengths are all different. They're not the same strength. These are just different strengths. These field lines are just a direction that another smaller magnet would align along. These don't actually give you, like, these are all different values of strength, and it's just a direction that another magnet would align along. It doesn't actually give you that much like the isopotential lines. Anyways.
You can see these patterns if you sprinkle iron filings around
Yeah,
it.
that's basically what it is. Basically, it's just a pattern iron filings show. It's not. So I wouldn't call them a magnetic field because it doesn't give you much info. An actual magnetic field would be the contours, like similar to a pressure map on a weather map. Is the more applicable, anyways.
The filings line up neatly along these invisible field lines. When opposite poles of two magnets get close together, their field lines naturally flow from one magnet to another, creating a continuous loop, a stable, lower energy state. Nature loves lower energy, so this configuration pulls the magnets together.
All right, so basically when it's aligned lower energy, Momo Jumbo. I can't find Benefactor on YouTube. Yeah, you're saying Benefactor wants to join the show? Well, yeah, just send some info, put it on the MES links, and we'll have a go.
When two like poles.
But again, here at MES, if you have an experiment that is mind-boggling, that's where I go. Or a easy to grasp physics anomaly, like similar to Fractal Woman has done with isopotential lines. When it's not an anomaly, just a better explanation. But actually, it is an anomaly with the quantum light photon moment.
Each other, their field lines clash. They don't flow smoothly into each other. But
all right, so we have imaginary field lines hitting each other. All right, so we have not actual thing yet, but he keeps going on. So let's see what he keeps going on.
Push against one another, creating tension or pressure that drives them apart. This is the standard explanation you'll get in high school and some college courses. But since you're watching my channel, I know that like me, you would find that explanation highly lacking. What's really going on at the quantum level? So let's go real deep right now. First, what exactly are these field lines? At the deepest level, magnetism is explained through quantum electrodynamics, or QED. QED is the theory that describes the electromagnetic force, which is one of the four fundamental forces of nature. It is perhaps the most well-understood theory in quantum mechanics.
There's another part here. They view strong force, weak force, gravity, electromagnetism all separate. Okay, and I think that's all ether interactions.
Fundamental forces of nature. It is perhaps the most well-understood theory in quantum mechanics. I have a couple of videos on this. I'll leave a link in the description if you want to know the history of QED and how some brilliant scientists figured this out. According to QED, magnetic...
And going back here, so you know how they have it all separate, but if the magnets in repulsion are actually dropping slower in gravity, if it's dropping slower in gravity like the Atwood machine, then it's like, where's my Nobel Prize? imagine they actually give me a Nobel Prize. They'd be like, I'll be smeared all over the news. CNN would be like, a conspiracy theorist wins Nobel Prize, and now there's a rising protest to boycott the Nobel Prize Committee. Alright, anyways.
I have a couple of videos on this. I'll leave a link in the description if you want to know the history of QED and how some brilliant scientists figured this out. According to QED, magnetic forces result from the exchange of tiny particles called virtual photons.
Oh my goodness, all right, we have virtual photons, guys.
These virtual photons act as messengers, constantly exchanged between charged particles and magnetic poles, communicating the electromagnetic force. Imagine two people in boats tossing a ball back and forth. Each time the ball is thrown and caught, they push each other apart slightly. Now imagine these two same individuals throwing boomerangs to each other. Each time they do that, they move closer together.
It's like so close there. Just do the paddles themselves will make them closer. Okay, so now we got boomerangs. We have virtual boomerangs, virtual particles.
Virtual photons are like invisible balls and boomerangs exchanged between magnets, resulting in attraction or repulsion. This virtual photon exchange is something that all charged particles do. That's what a charged particle is. Why do they do this? What is a charge? We don't know.
All right, let's go. We don't know. The most honest answer I've ever seen from a mainstream physics one. All right, Tammy says, Ben would love to join. Okay, epic stuff here.
Know that it's a property that some particles possess, and we know how that property works.
All right, so we don't know what negative
virtual particles before. You're probably familiar with regular photons, which are packets of energy that make up light waves, but they can also exist as small quantum fluctuations of energy in the vacuum. These are exchanged between particles interacting via the electromagnetic force. In this case, they're called virtual because they exist so briefly, popping in and out of existence, that they can't be measured.
Okay, so basically, virtual photons are like photons, except they just get out right away. So in other words, it's a vibration in ether that doesn't result in a standing wave. And speaking of boomerangs, I actually have a boomerang. Say boomerang. I actually have a boomerang. Boomerang. So we'll go this one here. Get boomerang. Search it up. Boom. Okay. I thought I just had I uploaded a boomerang video. Where did it go? Boomerang. No, this what is this? Oh, this is boomerang. Okay, this is the boomerang. Okay, we'll play this one out as well. Okay, we'll play this. But I thought I could have sworn. Okay, I could have sworn I had a boomerang video uploaded on this boomerang. I could have sworn I had it. Okay. But anyways, I had a boomerang. I have a boomerang. It's I was very good at throwing them. Yeah, it's hard. It's hard to, especially once they get like the bending gets different. But anyways, here's boomerang. Here's boomerang in Xena Warrior Princess. Here, look at her chakram scene. Well, let's see her boomerang. All right. What in the world just happened there? All right. So that's the boomerang. Okay. Anyways, let's go back to this guy. This guy's talking next level stuff. So he doesn't know what charge is. Now he's talking about virtual photons, basically coming in and out of existence. And he's saying that that's what mediates the electromagnetic force is light. That it pops in and out. This advanced tech boomerang. Yeah, I've seen a epic show.
Why do they pop into and out of existence? It's a consequence of quantum field theory, or QFT.
Okay, so now the ether's back. All right, we have the ether back, guys. They tried to run away from the ether. Ether's right there. There's little... All right, anyways, we are back in the show. So we got back to the ether. So there's ether fluctuation particle. It's just a just standing wave.
Which is the best and most proven theory of reality that we have. I have a couple of videos on this if you want to know the details, but to summarize, in QFT, all fundamental particles are excitations in quantum fields that are...
Yeah, so all are just excitations in quantum fields, but the things that have different fields all intertwined. That's an interesting aspect. Might be some truth to that.
We're in space-time, but these fields are not static. Even in the vacuum of empty space, with no matter or radiation, it's teeming with virtual particle-antiparticle pairs being created and destroyed constantly.
So in other words, basically just ether fluctuations. Just basically, it's the way there's constant waves, standing waves, and that exist for short period of time. Some longer ones, which we call particles.
Well, particles are not just theoretical curiosities. They mediate interactions between real particles. For example, when an electron emits a virtual photon, it can interact with another charged particle, effectively causing a force. The virtual photons are not measurable.
So one way could be this. This could be vibrating, and that's pushing the ether there. So that the actual virtual thing being pushed is just the wake of these vibrating, like standing waves.
Force. The virtual photons are not measurable directly, but we can measure their effects. Now,
so you can measure them directly, but their effects. Okay, that's getting interesting.
Satisfied with what you've heard so far? You don't need to watch the rest of this video because now
You're satisfied with what?
I'm going to go rabbit hole quantum on you. I'll explain things as deeply as I think we can go. So here's the in-depth explanation from a purely quantum mechanical perspective. At its most basic quantum level, magnetism comes down to electrons. Electrons exist in clouds of probability around the nucleus of atoms.
All right, so now we have probability is being thrown in there.
The clouds represent the probability of finding the electron somewhere there if we were to measure its location. These clouds of probability are what we call an atom's orbitals, which describe possible locations for the electrons. And what we call shells are groups of orbitals containing electrons at the same energy level.
Okay, now, and going back here to these orbitals, again, why I say the magnetic field, these resemble the isopotential lines right here. And in isopotential lines, it's just magnetic field lines, but where all the strength, you just graph the exact same one. So here's, so mainstream magnetic field is just this, where it lines up with the iron filings. And then the actual, the isopotential line is where the strengths are the same. So if you were to plot the exact same strengths everywhere, you're going to get a bubble like this. And again, like I stress this enough, this is from Fractal Woman. So at the bottom here is just the magnet right there with isopotential lines have all the same strength magnetic field that resembles these orbitals. And then different positive, negative charge. And you'll have, again, the same setup as these. Exactly, literally exactly. It's just it. There's no other way around it.
For the electrons. And what we call shells are groups of orbitals containing electrons.
Oh, Stephen F is in the show. Let's go.
At the same energy level. These electrons have two important intrinsic quantum properties that are important for this explanation.
Okay, 29,000 tons. What's John's philosophy on magnets? Yeah, that's a good question. I think I've asked before. It's like he yeah, didn't have any like concrete thingy. But he did like my everything's just ether vortex thingy. So he did like that. So yeah. I'll have to ask him exactly next time he's gonna be on the show next week, so you can ask him there. He's gonna be on the show. Yeah. Anyways, let's go again.
They have a negative electrical charge and they have a quantum spin. But mathematically, electrons are approximately.
So again, notice the spin. The charge could be vibration. This could be rotation. So again, rotation up or down. Yeah, basically, yes. You just turn it upside down, it becomes a downspin.
Mathematically, electrons are approximately tiny particles orbiting the nucleus of atoms, and they are approximately spinning, like you see in this animation. The spin can be up or down. Because electrons have an electric charge, their spin creates a tiny magnetic field. So each electron acts like a miniature magnet. Its spin orientation determines its magnetic poles. The crucial quantum mechanical detail here is that
notice I said each one is a magnet.
So each electron acts like a miniature magnet. Its spin orientation determines its magnetic poles. The crucial
and then going back here, isopotential lines of a magnet is isopotential lines of where do you find these electrons in their orbitals around atom.
Quantum mechanical detail here is that the electrons obey something called the Pauli exclusion principle. This principle, simplified, says that two identical electrons can't be at the same place at the same time. And this is the key to understanding why materials become magnetic in the first place. But first you might ask, what's the basis of the Pauli exclusion principle? Why can't two identical electrons be at the same place at the same time? This has to do with their wave functions. All fundamental particles are essentially waves, defined by wave functions which can be calculated using the Schrödinger equation. Approximately, the square of the wave function of an electron represents the probability of finding the electron in a certain location.
And the reason they square it is just so that you have all positive values, because you can have the same location going up and down. This squared so it's all in the same positive axis.
The wave functions of two identical electrons interfere or combine in such a way that their wave function becomes zero. You can think of this as the probability of finding them together becomes zero. So this is just not going to happen. Since for a given orbital, electrons are identical to each other except for their spin orientations, you will only find oppositely spinning electrons together in any orbital of an atom. In materials where all electrons pair up, one electron spinning up paired with another electron spinning.
Anyways, this is getting like ridiculous amount of stuff. Here's iron lattice. Let's just go back here. So basically you have the spin direction, but it's not spinning. You have a magnetic field, which is imaginary lines of something that causes forces together, and it's mediated by virtual photons or excitations in the ether.
Adjacent atoms, such that
beneficent TV. Interesting. Okay.
Parallel spins are favored for the material overall, which results in an overall magnetic effect on the metal. So now we know why some metals can become magnetic, while others cannot. Now the remaining question is, why do magnets sometimes attract and sometimes repel, depending on how you hold them? It boils down to the spin alignment and quantum symmetry of electron wave functions in the magnets. When two similar poles approach, north to north, south to south, their electron spins are aligned in opposite ways relative to each other. One magnet has electron spins oriented up and the other magnet oriented down relative to it. In quantum mechanical terms, this arrangement creates interference patterns in their electron wave functions, making it energetically unfavorable for electrons to occupy overlapping states. This opposite
and notice here, the north-north, yeah, this is, but these should be aligned. Yeah, this is, so they have the spins in a different setup there. Okay, this is opposite spins. I'm trying to think, why would this be? Okay, this is this way aligned. South-south pointing this way. I'm trying to think. They should hit each other. Okay, so we have this is like opposite of what I envisioned. So this is not attracting.
In quantum mechanical terms, this arrangement creates...
But no, but why is this pointing north? Okay, it's pointing south there. If that's spinning this way. Yeah, this is the wrong direction. Okay, this is why. This spin is in the wrong direction. Because look, if your thumb is the south, if your thumb is the south, then this one curls around this way. But then if you flip it, this would curl down. So this is I think they made a mistake here.
In quantum mechanical terms, this arrangement creates interference patterns in their electron wave functions, making it energetically unfavorable for electrons to occupy overlapping states. This raises the energy, making the system want to avoid that state, causing them to push away. The electron wave functions from one magnet interferes negatively with those of the other magnet. A higher energy state is created in the space between the two similar poles. The materials want to avoid that space and move to a lower energy space. It's like the two magnets going down a function interference patterns, controlled by spin alignments.
Oh no, yeah. So I think this is just based on the spin, not based on this pole charge area or something. This is always pointing up. The spin could be down or up, but then they don't switch to the polarity. So the polarity does that not affect it in any way? So this one is spin right, and this one's spinning up. This looks like it should collide. Yeah, this is what spooky actions of distance looks like. Yeah. The spooky action is yeah, basically ether fluctuations. Just like you can connect them at a distance because it's just a wave, possibly. Yeah, that's a good question. I haven't looked at that. That might be for a future MES live stream. Wednesday ones. We'll ask what is spooky actions at a distance, just to see what the mainstream is. This is the mainstream stuff here. Let's see the summary, and then we'll go over to what I actually think is happening.
Leave you with. Electron spin creates tiny quantum magnets. Exchange interactions align electron spins in the lattice structure of materials like iron. Aligned spins produce large-scale magnetic fields. Magnets interact through exchanges of virtual photons, which are excitations in the quantum electromagnetic field. Attraction and repulsion results from how electron spins and wave functions overlap and interfere quantum mechanically. I hope this gives you a deeper understanding.
All right. 11 days ago, 270,000 views, and it's like, well, and we got nowhere from it. But basically, understand a bunch of stuff. And again, going back here, water magnets attract or repel. Just look at this right here. Rotating magnets in water behave like magnets. I'm rotating cylinders.
Here we have two identical cylinders completely submerged in water and connected by two flexible hoses to two...
Okay, this one here, Tammy says, I also shared a video of a soccer interview of a person who has ability to invest in this project. What project exactly? If someone other than me influences him enough. Yeah, so if you can get him on the show, and if he has a bunch of money. Which project are we looking at? I have many projects to invest in, and so on.
Two identical electric motors. The electric motors will be driven by a common 12 volts.
Also, I just noticed there is Uncle Murray on Odyssey. Okay, Uncle Murray's on Odyssey. We have no comments on Rumble. One comment on here. No comments on BitChute. And let's see if this one has any comments here. Whoops. Okay, let's go back here. No comments or anyways, it is all good. Let's go back here. Leave Odyssey's opened. So Odyssey first comment on non-YouTube. All right.
In this experiment, we're going to start the motors, which are going to rotate the cylinders in opposite directions. Let's see what happens. We start motors now.
Yeah, I'm lowering my desk with my auto standing desk. Unbelievable. Yeah, so you can see right here, this is in opposite directions, they attract.
We see that the cylinders attract each other and now are sticking to each other. Let's try to separate.
Yeah, so in other words, there's actual spin, ether spin, quantum fluid spin, whatever you want to call it. Whoops, my alarm just went off. Oh, I forgot to turn this on. Okay, anyways, my alarm off for noon, so we're going to end the stream once I finish this video. Alright, so that was an attraction. Now we're going to go to the repulsion one. So it's still sticking.
See them back to their original positions. In this experiment, see what happens.
So now it's spinning the same direction. So when it's spinning the same direction, these collide. The water molecules collide. So in other words, the virtual photons collide.
The motors now.
So and then the spin itself creates this the virtual excitations in there. So again, virtual photons are actual ether wakes.
We observe that the cylinders repel each other. Their relative distance is increasing. Let's try to push them against each other. See if we can.
Tammy says she wants to share a link here. Well, you can share it in there, or otherwise I'll have to give you a moderator setup here. So you can put the comments right here inside the thingy, and I'll then let me know you have it there. Otherwise, I just make you moderator because you have. Okay, let's put you a moderator. As moderator, so you can put like standard moderator, and then yeah, again, don't abuse your standard moderator; you'll also get kicked out. All right, you can share links now, Tammy. I think I made yours. Okay, yeah, this is standard moderator. Okay, yeah, there's. Let's continue. On here, let's finish the video. Let's go. So this guy's basically saying virtual. So here's the mainstream one: electron spin creates tiny quantum magnets. Exchange interactions align electron spins in the lattice structure of materials like iron. Aligned spins produce large-scale magnetic fields. Magnets interact through exchanges of virtual photons, which are excitations in the quantum electromagnetic field. Attraction and repulsion results from attraction and repulsion results from how electron spins and wave functions overlap and interfere quantum mechanically. Anyways, 20,000 times this video is way better than the previous guy was such a waste. Yeah, but this is the mainstream one. These are mainstream. Okay, when you got a million subscribers like that, this is the mainstream. I'm just saying this is what the mainstream is, and this is what I actually think is happening.
Reduce the distance.
Yeah. Tammy says David Butler makes nice videos, but quite limited. Interesting.
What happens if we reduce the distance? Well, it's quite difficult to make them approach each other. We see that there is a force which is acting so that they.
Yeah, so magnets, this is what in spinning and repulsion, spinning the same directions, hit each other and they want to separate.
Repel each other. This force is obviously due.
Okay, Asher says the water experiments very interesting. Wonder what happened with 4 rotating discs instead of just 2. Yeah, it'd be interesting. I think you could also do something similar with sound. I think you'll get just what magnets are.
Motion of rotation.
Okay.
Let's start.
2 cylinders. So now we have 2 cylinders. Now we have it's spinning. And this is okay. This is you call it spin up. This is north, the south. North is wherever the thumb is spinning. Okay, so that is the spinning there. So yeah, this resembles. This is to analogy of a magnet. Cylinders are aligned together and enclosed with styrofoam. Using a right-hand rule convention, the curl of the fingers indicates the direction of the cylinder rotation. Yeah, I'm gonna put this right here. Again, this is real physics. Like, again, this is just helps elaborate what in the world's going on. And the thumb corresponds to the north pole of a magnet. The light green side is north, and the yellow side is south. Opposite poles attract for both the cylinders and magnets. Okay, these are opposite poles, north, south, and this one is spinning. So then, north would be like this. Other one would be spinning, yeah, this way. So the spins align. When the spins align, they do that. So this one is yeah, it's like spinning around it, but it's still going towards it. It's going towards it. And then it's hitting each other. Poles repel, and the same behavior is observed for both the cylinders and magnets. And notice he added these weights here just so that it's all pushed, so that's the string is straightened. Anyways, so he puts that in. This is in repulsion. Notice what happens. North, north, south, 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 north, north, and they move around. And magnets. Yeah, and there it is, and it goes there. And then they flip. They flip, and then also even if you put the repulsion on the side, they still flip. So south, south, north, north, and then because notice the spins will collide with each other. Placed on their sides with like poles parallel to each other, both the cylinders and magnets repel and behave the exact same. And also just flip over. They flip it so that they have the opposites attract. Yeah, and lastly, again, is a magnet just a vortex in a fluid-like substance called the ether? Oh yes, yes, it is, or the quantum fluid. All right, so that's quantum fluid, and then this one here I also included this. I have to stress enough. Again, it's all. Compare this with the other guy's one. This guy's saying a bunch of literally quantum mumbo jumbo, and the only actual demonstration he had was a virtual demonstration of a boomerang and a person throwing a ball. It's like, all right, like what? And now this one is, if you spin clockwise, a metal spinning top, and then now if you have a plastic spinning top, which doesn't have as much momentum, so it dies quickly. So this is spinning clockwise. They're both spinning clockwise. They hit each other. It's gonna die. They're spinning top. They strike each other, so they don't like each other, and the glass is curved down a bit so that they go up. They force together. So that's why they're hitting. So it doesn't like it, so it's gonna lose its spin speed. I just want to show this because it illustrates the idea of spins. Just spin different way. Spinning top falls first. Now spin it opposite. Spinning top counterclockwise, and then it spins line up. So this actually makes it spin the entire time. So now plastic gains spin speed from the metal top. So now it's like they become one. They become as one at 5 times the speed, and it doesn't die, even though it's about to die, and each time gets sped up by this. So this gives the idea of how magnetic domains is just a bunch of electrons spinning, and then they all spin in unison with ether. Okay, there it is, and they all fall at the same time. And then the last one is this one here. Actually, we'll keep going. Yeah, this is part of the MES physics playlist right here. So this MES physics playlist. I put all the experiments that are related to this. I should put in the magnets. No, actually, the magnets and repulsion. We'll do that maybe later. So anyways, so this one is mechanical demonstration of inertia. Going back to the magnetic domains, you can actually physical analogy. This is probably the first one I've ever seen. So you have a bunch of little gyros, and then if you have an external torque applied, they all align the same one. They all align with external torque. Okay, so initially it's hard to push. So spinning them up. Yeah, so this is a demonstration of mechanical rendition of inertia.
The actual mechanical rendition of inertia. Nobody's ever seen inertia. What's going to happen in location? And
Yeah. So notice right when he pulls it, I'll mute it. Right when he cranks it up, you'll see them turning, and then it goes freely. Yeah, it turns and then it goes. So you can feel that's the inertia is the realignment of the gyro domains of the, and then now you have it's free flowing, and then once you let go, all of them go all over the place, and now you have to go to again, torque it again. So now you have to torque it again, and yeah. So once you torque it again, they all spin, line up the same thing, and go. And that's similar to this one since we talked about gyrostops. So here's I wanted to show here just to I want to compare how tippy top, phi top, and gyroscope rise just rising. It's very interesting. So here's a tippy top. It's like a mushroom and it just goes up. So this rises on its own like that, and now you have an egg there. Next one's an egg, 5x speed, and just see it going down. I wanted to illustrate a few things. And the next one is the egg. Okay, so now the egg. You spin this up. Again, so mainstream one says that it makes torque with the ground, the friction on the ground, which is completely opposite of the Action Lab guy. Action Lab guy was literally using deception there. There's no other way around it, because it's not because the spin speed's lower. It's because the mainstream says it's because it's a torque on there, but the gyro is because the spin speed's lowering. But that disproves this. So it's like it doesn't matter how you spin it. He's lying, or just clueless because you can't even find it anywhere. You can't actually find the explanation for how gyros rides on its own. And then this one is a fake explanation because gyros disprove it. Okay, this is now the last part I wanted to show this part again. It's to do with the external torque gyros lining up or magnetic spin domain lining up with the external magnetic field. Okay, this is falling down. All right. It looks like it's going backwards. This is the cool thing about the video camera frame thing. So notice how it's spinning, and now it looks like it's gonna go backwards, just because the frame rate starts matching up with the camera. So it's going this way. Now it's gonna look like it's going backwards. Yeah, no, it looks like it's stopped and going backwards. That's actually just the frame rate. All right, so that's amazing. And it's doing that again. See, whenever it matches up with the frame rate, as it's slowing down, it looked like it changes directions. So that's absolutely fascinating. Okay, now we have this one here, 2 degrees freedom gyro. So here it is. Here's one I found. The reason I upload is pretty interesting. When it's not spinning and I push this, it wants to align vertically for some reason. Now it's going vertical. So like, why is it aligning vertically? So look what I just did. If I torque it quickly, it goes up. It aligns up vertically. But if I spin it, it doesn't go up vertically. It goes in line with the direction. So gyro spin lines up with the applied torque. So now if I split it, when it's spinning, it lines up. When it's not spinning, it goes up vertically. So it's like, all right. And then if I go reverse direction, it reverses completely. We need to be a 501 charity. I've discovered your channel with beneficent. Okay, interesting. Yeah, 2 people cannot stand at the same spot at the same time either. Okay, this one here lines up with applied torque. If I go in a direction, it doesn't go. But if I go reverse, it flips it over until it's spinning the exact same direction as the torque. So again, I think this is the key. Everything's yeah, but you can spin this opposite, but it's unstable. The second there's a slight nudge, it'll flip over upside down. This one's actually pretty fascinating. Yeah, I didn't realize. Yeah, I forgot that the thing goes up for some reason. So it's like I always look at these little things. Anyways, that is all for today. Hopefully you join, and yeah, get that beneficent guy, get him on here, and so on. Well, you can add links now. You can add links right here, Tammy. Anyways, thanks for joining, and have a great day. All right, and then post it on here. The only one that had a comment was this guy, and you get that, and so on. All right, epic stuff, guys. There's no other comments here. All right, let's close this. All right, guys. Anyways, thanks for joining, and have a great day. And yeah, Ashtray, cool stuff. Yeah, definitely check out those out. Check the MES Physics playlist. It's again extremely valuable stuff. Yeah, especially this one here, the Planck's constant is a quantum of energy, just a quantum of action. So this one here, I'm definitely 100% certain there's a bug in the quantum physics where you get a million different types of photons and so on. It's actually just ether fluctuations. and so on. So I'm gonna put this here. Biff doesn't take my science seriously. Okay, Biff. Okay, now that's who's Biff now? You get a whole bunch of peeps. Anyways, to get the names in properly. Anyways, guys, that's all for today, guys. And I'm ending the stream in 3, 2, 1. Hopefully you enjoyed. Anyways, check the MES physics and also donate because I gotta pay now $15 a month for this Prism Live Studio.